Okay, so last time we started to go over from the combinatorial description of freeness to maybe more analytic. In particular, we want to understand one of the basic problems, the free convolution, which is the distribution of the sum of free variables. And up to now, we have a machinery for dealing with moments, or maybe with cumulants. But if one really wants to do concrete calculations, one needs a more analytic machinery. Okay, and I mean, the last chapter we encoded this relation between moments and cumulants into a relation between form and power series. But we want to go in the direction that those form and power series really become analytic functions, and then we have at our disposal analytic machinery. I mean, there are many results about analytic functions which are quite powerful, which we can also use for doing calculations. And the first thing we're doing is, so really, I mean, we are shifting somehow from looking on moments. I mean, that's in our algebraic probability spaces, the moments are the crucial ingredients. Oh, okay. But if I have one self-adjoint random variable and the moments have the right growth, then actually the moments can be identified with a measure. So actually we are now talking about measures. And measures are much more analytic objects. And we will formulate things on the level of measures. And at the moment, it's measures which are compactly supported, because only this gives a one-to-one correspondence between moments and measures. Okay, and then last time, I collected a lot of things, how we have this connection between moments and measures. And I also wrote down the theorem which transfers the question of how to add free variables from the level of moments to the level of probability numbers. So maybe I recall the theorem which I wrote down last time, which we still have to prove. But last time I collected all the ingredients for proving it. Okay, so it's talking about probability measures. So mu and mu are two probability measures on R, and they should be compactly supported for now. So let mu be two compactly supported probability measures. On R. And then we want essentially, we want to see mu should be the distribution of a self-adjoint random variable, mu should be the distribution of the self-adjoint random variable, and then we want to see what is the distribution of the sum of them, if they are free. Okay, so this means we should realize the situation by variables which are free, and one of them has mu as a distribution, and one has mu. Okay, that's the main statement here, that actually we can do this realization. So then there exists star probability space. If you want probability measures for the moments, so there exists defined star probability space and elements in this space, so two of them, each of them should be self-adjoint. So x is equal to x star, y is equal to y star. Those are random variables, such that the first random variable has as a distribution mu, so the moments of x are given by the moments of this measure mu, and the moments of y are given by the moment of the other guy. So x is equal to mu of y is equal to mu, and furthermore, we have realized the variables x and y such that they are free in this probability space. So x and y are free. Good. Okay, and then we are looking on x plus y, a basic operation which we can do with our operators, and we ask about the distribution of this. Okay, and the distribution of this is actually again a probability measure, because the moments of x plus y, they satisfy what we had before, namely they are exponentially bounded. So this means there's exactly one probability measure which has those moments of x plus y plus its moments. Moments x plus y, so phi of x plus y to the power n, the collection of all those guys. Of the self-adjoint, those are the moments of the self-adjoint random variable in the x plus y, because x plus y is self-adjoint, x and y are so. Okay, so those moments are exponentially bounded. And that's the main thing which we need if we have the moments of a self-adjoint variable in the star probability space. Then the moments should be exponentially bounded, and then we saw last time they correspond or they determine uniquely a probability measure. So they are exponentially bounded. Hence, determine uniquely a compactly supported probability measure. Compactly supported probability measure, namely the distribution of x plus 1. Okay, this is again a probability measure on R with compact support. Okay, and furthermore, last time, this outcome here, namely this measure here, does not depend on the concrete realization of x and y. Right? It only depends on the fact that I have a variable whose distribution is mu, I have a variable whose distribution is mu in a star probability space and which are free. Of course, I can find many different x and y in different spaces which might have this property. But the outcome does not depend on this. So this means this mu of x plus y in a sense is uniquely determined by the mu and the fact that I want to realize x and y to be free. Okay, so does not depend on concrete realization. Good. Okay, and then of course, so this is what clearly we will call the measure which we get here is what we call the free convolution of mu and mu. So I also wrote this down last time. Just this. Also, we denote this by mu plus in the box mu. We call this the free convolution. Because the corresponding classical problem for independent random variables is exactly the classical convolution of measures, of probability measures. Good. Okay, but so we should prove this, but the proof of this is essentially just, collecting or using effects which we did last time. And maybe something which you had to do assignment. Good. Okay, so this means I should realize those measures by operators. Okay, if you have one measure, we can realize this. That was what we did the theorem before. So we can realize each of them by itself. So we can realize the measure mu as a distribution of some variable x. And I can also realize mu as the distribution of some variable y. If I'm just taking, for x, I'm just taking polynomials in x, and I'm just defining the state by the moments of my measure. That's what we did last time. So I can realize x, the probability space, which is given by polynomials in x, supplied with the state phi x, which phi of x, or polynomial is just integrating with respect to the measure the corresponding polynomial. And y in the same way, we can realize on some other sub-probability space, and the polynomials in y, supplied with this phi y. Okay, but now of course the point is I want to realize those guys in one space such that they are free. This of course is a kind of free product construction which we have to make, which I mentioned or addressed a few times during the class, and of course it's important that we have such a construction. Okay, and I don't want to do this explicitly or in detail during class, but in the last assignment you were asked to look on the corresponding chapter in my book with Andro, where this is made very precisely. So there's a construction that if you have star probability spaces, you can take a free product such that essentially those guys are embedded and those two copies which you have are free in this space. Okay, so essentially this is this exercise from the assignment. So this tells us so that we can take the free product of those two spaces. So we 6, x is 4. And this means we are getting a new star probability space. And I mean, the really non-trivial thing is the positivity. If you just want to do this on the linear level, then this is more or less quite easy to write it down, using more or less the definition of freeness. But to check if you have something positive here and something positive here, that you also get something positive under this construction, essentially reduces, I mean, to the fact that the Schur product of two positive matrices is positive. The Schur product of matrices is if you take entry-wise products. This is a classical result which is not too hard to prove. Okay, so I mean it requires a little bit, but it's not really too hard to see this. But in any case, it is true that we can take this free product and then we get a new space, and there we have our operators x and y. So thus we realize x and y in this free product space, and the free product of variables of polynomials in x and of polynomials in y are just polynomials in x and y, where x and y don't commute. And then you just put, of course, the corresponding state on this. So these are polynomials in x and y don't commute, and we have a state there, which is the free product of those two guys. Okay. So we have those variables there, such that the variables are actually free in this space with respect to this state. Such that x and y are free with respect to phi x star phi y. And of course, the distribution of x in this space is the same as it was in this space, because the moments of x in this space are the same as the moments of x in this space, and for y the same. So we have essentially copies of x and y, but in a bigger space, I have both of them at the same time, and so I can also talk about their sum. I mean, in this setting, of course, I cannot talk about the sum of x plus y because they are living in different spaces. Okay, but this is embedding. I can do it, and then I can control their moments. In particular, x plus y now have moments in this space, and of course, the moments determine the probability measure if I can be sure that the moments are exponentially bounded. Okay, that's the only thing which I need, and what is clear is that the cumulants are exponentially bounded, because the cumulants of the sum are very easy. So that's one of the main points of the cumulants. Calculating the cumulant of x plus y, x and y are free, is not so easy, not so clear what this is, but the cumulants of x plus y, they are very easy, because mixed cumulants vanish for free variables. So they are vanishing mixed cumulants in free variables, just the following. So namely, what are the cumulants of x plus y? So the nth cumulant of x plus y, so this is take my cumulant functional, and for each argument I'm plugging in x plus y. Each of them is x plus y. Those are cumulants of x plus y. But now, of course, the cumulant functionals are linear in each of its arguments. So this is just the sum of terms where I just choose an x or an y for each argument. So I get 2 to the n terms. And of course, one term is the one where I chose only x's. So this is n of x, x. Then I get one term where I only choose y's, up to y, and then I get many terms where I have some x's and some y's. But cumulants in free variables, mixed cumulants vanish, so this means all those terms are 0. So there are a lot of other terms, but actually they are all 0. So you see, on the level of the cumulants, x plus the sum of free variables is very easy to describe, because the nth cumulant of the sum is just the sum of the nth cumulants. This is kappa n of x, that's kappa n of y. On the level of the moment, of course, this is not true. Right? It was one of our starting problems. I mean, what is the moment of x plus y if x and y are free, and I know the moment of x and y? It's a complicated polynomial, which which we were trying to understand. We put some structure into it by seeing that non-crossing partitions govern somehow this. But the best way to see how it is governed is really to say we should go over to cumulant, and then it's just everything. Yeah, good. Okay, but now we know x, the moments of x, and the moments of a compactly supported probability measure, which means the moments of x are exponentially bounded. And then we have seen last time that this also means the cumulants of x are exponentially bounded. The same for the kappa of y, they are also exponentially bounded. And of course the sum of two things which are exponentially bounded is also exponentially bounded. This tells us the cumulants of x plus y are exponentially bounded. And this means the moments are exponentially bounded, and then we know it must be the moments of a probability measure. So we're really coming back to the probability measure. Okay, so these cumulants are exponentially bounded. And because we have seen last time that exponentially boundedness is the same for moments and cumulants. So we can go in both directions. One of them is exponentially bounded, also the other is exponentially bounded. So hence, moments of x plus y, of x plus y to the power n, are also exponentially bounded. Okay, thus they must be the moments of a compactly supported probability measure. Probability measure on R. I mean, that was what we saw last time. Or what I told you last time. Huh? Okay, and so I mean, this is the measure which we denote by the mu of x plus y. Good. And of course, I mean, what we are doing here, I mean, the outcome of mu of x plus y, the moments of x plus y only depend on the moments of x and the moments of y, and the fact that x and y are free. I mean, that's something which you already saw at the very beginning, that if I want to calculate moments or any mixed moment in x and y, it is uniquely determined by the moments of x and the moments of y into freeness. No? But in this setting, it doesn't depend how I have realized my x and y. As long as the moments of x are the moments which are prescribed by mu, and the moments of y are the moments which are prescribed by y. So we know that the moments of x plus y are determined by the moments of x, by the moments of y, and by the fact that x and y are free. Freeness in x and y. So this means that this probability measure here is just determined by this. No? So this, it is clear that what we denote by mu, free convolution is mu, which is the distribution of x plus y, which is the probability measure which has the moments, which has as its moments the moments of x plus y, that this depends only on the moments of x, or the probability measure, which has those moments, but this measure is mu, and it depends only on mu y, but this is to be mu. It does not depend on concrete realization of x and y. Good. Okay, so let's just bring everything together. Essentially, I mean, it's just making a shift from moments to probability measures. But in a compactly supported case, I mean, there's a very clear relation. No? So it's really the moments determined by probability measure. Good, but now we have an operation on probability measures. And of course, we want to understand this better, and in the end, we also want to be able to do calculations. No? And so let me make first a few remarks or simple properties of this operation. So what I have here is a binary operation on probability measures. For two probability measures, I get a new one. So this is a binary operation. Binary operation. Yes, of course, it's free convolution. This is an operation on compactly supported probability measures on R. So this has a couple of quite straightforward properties. So it has following properties, and those are easy properties, so that's easy to see. So first of all, it's a commutative operation. So mu free convolution is nu is of course the same as nu convolution is mu. So this operation is commutative. Plus mu is the same as mu plus mu. Because if I take x plus y, and x as distribution mu and y as distribution mu, and I can also, because x plus y is the same distribution as y plus x, and then y is distribution mu, and the same distribution mu. Okay, then of course things are associative. So if I have three probability measures, then I can take first the free convolution of two of them, and then the free convolution is the other, but I can do it in different orders. And this is of course the same. So this is associative. So this means U1 free convolution with U2, free convolution with U3 is the same as if I first do the free convolution between U1 and U2, and then the result of this I convolve the free sense is U3. And of course in the background is this kind of associativity properties of the freeness property. Of course here I realize my three guys by variables x, y, and z, which are all free. But if they are all free, then of course the set generated by x and y is also free from the set and other combinations. So this is in the background there is this kind of associativity properties of the free convolution which you also saw in some assignment. Good. Okay, then this operation also has a kind of zero element, something which doesn't change anything. You can free convolution with it. And of course, I mean, what is this? Of course, on the level of operators, this must be zero. By adding zero to anything, I'm not changing things. And zero, of course, has as a distribution the delta at zero. The probability measure which has mass zero. Because all the moments of the zero operator are zero. Good. Okay, so this means zero element. And this is delta of zero. So that's a direct probability measure which puts all the mass at zero. Delta zero is the zero element. So this means the free convolution of delta zero is any mu is mu. Doesn't change anything. Okay. And instead of delta zero, one can also look on deltas at other points, where I'm putting mass at some other point. And of course they are realized by a constant, and constants are free. So this means it really fits together that convolution with delta, let's say at point S, is just a shift of my probability measure y with a mod S. So the free convolution is the probability measure delta S. So S is a real number. And delta S is the probability measure which has mass 1 at this point S. This has the effect of shifting measure by the amount over by the amount S. So this delta of S, free convolution, this any mu is something which I call mu S. This mu S is just a shift of this mu by S. So this means mu S of some, let's say, Borel set is just the mu of the shifted set, just B minus S. And with this I just mean the set any element B from here and shifted by this fixed amount S in B. So this is for all Borel sets. Okay, this is just shifting. Okay, I mean this is hopefully clear. I mean maybe you should think about this, what if this really is the case, but this is depends just on the fact that delta S is the distribution of S times 1. Okay. So you have 1 times S. All the moments of this are just the powers of S, which are the moments given by this. Okay. And 1 is free from everything, so I really can take the 1 in my space where I realize the x here as the free guy, and then I have here essentially the variable x plus S times 1. And of course this has just a shifted distribution. Okay, maybe you might want to write this down for yourself. Good. Okay, but now really, so those are the basic things. I mean, but now we really want to understand better, and in particular we want to do calculations, and now we really should go over to an analytic description of probability measures. And for this, essentially we will encode the information about moments and cumulants in analytic functions, and essentially this will be the functions which in the last chapter were the formal power series. And we will rewrite them a little bit in the form which is maybe better for an analytic description. Okay, good. So I mean, in order to do concrete calculations in general, so we need analytic description of the free convolution. And in particular, we will encode information moments, cumulants in analytic functions. Okay, so it's some versions of the functions which we already had as just from the power series, but now we want to become serious and making them, consider them as analytic functions and really using tools from complex analysis for getting information about them. Good. Okay, and so on the level of the moments, actually the version of this moment series which we had is what is called the Cauchy Transform. Okay, so now I will introduce the Cauchy Transform and maybe give you the main information about this. So this is again classical theory where we know a lot. So I want to define it and give you the main information and give you ideas for the proofs. Again, I'm not going to do everything, but I want to give you these ideas. How this fits into classical considerations. Okay, and so the Cauchy transform is something which we define for a probability measure, and actually we can do it for any probability measure. Complex support is not needed for this. And that's of course, that gives us hope that actually also we can maybe extend this definition of the free convolution to arbitrary probability measures. If we just go by moments, now algebraic setting, then of course it's not clear. I mean, maybe we can go a bit further than this, but at least of course there are probability measures for which moments don't exist. And then of course we don't know how to define free convolution of such measures. If we have analytic objects which work always for any probability measure, then there will be hope. Okay, the Cauchy transform is such a thing. So namely this is defined any probability measure. So for a probability measure, usually I denote this by G. Maybe if I want to say which mu, then I put the mu there, but maybe if there's only one mu around, I just call it G. Okay, so this is defined. So G mu. So this is a function of z, variable z. Of course, this is really a complex variable. And we define it as the integral of 1 over z minus t. And I'm integrating t with respect to my measure mu. So that means t is running over the real line. Good. Okay, and of course, the question is, I mean, when does this make sense? Of course, I have here 1 over z minus t. And so if z would be real, then there would be problems. Okay, because then this might explode and it's not clear this integral gives the final value. And I mean, in order to stay away from these singularities, we are defining this only for z in the upper half plane. So really z is a complex variable, but it's in the upper half plane. And this means we are staying away from the real axis, and this really makes always sense. So this means this here is defined for z in the upper half plane, which I denote by C plus. So these are complex numbers. So z is not really a complex number, not just a formal variable anymore, but a complex number for which the imaginary part is bigger than 0. Also, we have the situation, I mean, so here's the real axis, on this my measure is defined, and then I'm defining this for, let's say, a z, which is in the upper half plane, and what I'm taking is 1 over z minus t, and z minus t, so I mean t is running here, and z minus t is this, and 1 over z minus t, I mean z minus t cannot become arbitrarily small. The problem would be if z minus t becomes arbitrarily small, then this will explode, but the length of z minus t, if t is running over the real axis, I mean the smallest thing I can have is this distance here, the projection of z onto the real axis. So this means for any z, this guy here is bounded, and this means this integral is well defined. Okay, so this means it makes sense on the upper half plane. And maybe I should also say, very often, people consider a variant of this thing, which is called the Stieltjes transform, but this is more or less the same. The difference is just a minus sign. So it's just a matter of maybe the community to which you belong. Right? Some communities, Cauchy transform is maybe the main thing. In some community, in particular in random matrix context, people prefer to talk about the Stieltjes transform. It's just a minus sign, so of course you can always translate from one to the other, but you should be aware which convention people are using. Because sometimes, maybe if you call it Stieltjes transform, you're meaning the Cauchy transform, or sometimes people are talking about the Cauchy Stieltjes transform. You really should check in which convention they use. Okay, so often, in particular, in random matrix context, considers also the following variant of the Cauchy transform, which maybe is denoted by S mu of t. So this is more or less the same definition, integral over R, but here I take 1 over t minus z. So just exchanging t and z, integrating over mu of z, and of course this is the same as minus g. So the Stieltjes transform is just minus the Cauchy transform. Okay, this is called the Stieltjes transform. Good. Okay, now in the next theorem I'm collecting the basic properties of the Cauchy transform, in particular properties which are relevant for us in our context. So maybe first part of it are just some of the basic properties of the Cauchy transform, in particular that it really is an analytic function. So it's really an analytic in the sense of complex analysis. It's a differential, complex differential function which opens
toolbox of complex analysis for us. Good. Okay, so assume I have the Cauchy transform. So G is the Cauchy transform. The Cauchy transform. The probability mu. Okay, and then one has following properties, which are all quite simple to see. So first of all, G, we define it as C plus, but where does it go to? Which values does it take on? And I mean, if Z is here, that Z minus T is also in the upper half plane, and if I take 1 over this, then I'm going from the upper to the lower half plane. And so I'm integrating over something in the lower half plane, which gives me something in the lower half plane. So the values which G takes on are in the lower half plane. Of course, this T minus is the lower half plane. Complex numbers whose imaginary part is strictly smaller than so. So it's really the open. C plus is the open upper half plane, and this is the open lower half plane. R doesn't belong to it. Okay, then the second part is the statement that it is analytic. So G is analytic on C plus, what is defined. Okay, and then it also has a kind of behavior what happens if the value of my argument goes to infinity. So maybe that's also good to know. So namely, what is the limit of Iy, G of Iy, if y goes to infinity? So y is here real. Okay, so I'm looking essentially on the imaginary axis, what happens if I go to infinity there, and then I mean this says that G behaves essentially like 1 over I minus. So it's, I mean, if I'm going to infinity, G behaves more or less like 1 over Z. Okay, so here this is precisely if I'm going on the real axis, so the limit of this is equal to 1. So G of this behaves like 1 over Iy. Okay, and maybe another statement in the same direction, where I'm taking y, I'm multiplying it with the absolute value of x plus Iy. I mean, I'm writing my set, complex set, as a real part x and imaginary part y. And I'm taking, multiplying the absolute value, the Cauchy transform, with the imaginary part, and then I'm taking the sum over all y's, which are positive, of course, should be in upper half plane, and x and r. So I'm taking the sum over all possibilities, and this actually is 1. So this means the Cauchy transform is bounded by 1 over its imaginary part. Good, okay, so those are kind of easy properties. I mean, we'll say a little bit about them, but they are easy to check from definition. And then maybe something which is a bit more complicated, but also not too much, but very important, is that actually, if I have this Cauchy transform, I can recover the measure from this. Of course, that's what I want. I mean, I have a probability measure, and probability measures are not so easy to understand. But I describe my probability measure, or I encode the information about my probability measure in a transform, a function. I mean, functions are much nicer things, in particular if they are analytic. Those are objects where I know a lot about. And of course, such an encoding is only a good encoding if I can go back. So I mean, of course, if there is a one-to-one correspondence, in particular, I should have an effective way, if I know the Cauchy transform of a measure, how do I get the measure? And this is given by what is called the Stieltjes inversion form. Okay. And of course, I mean, in classical probability theory, I mean, one does somehow the same, encoding information about my measures in a transform, but that is the Fourier transform, which is somehow important. So the Fourier transform goes somehow very nicely with the classical convolution. Here it will turn out that the Cauchy transform is much better behaved with respect to the free convolution. But in principle, it's the same idea that we encode the information about our measures in a function. which has some nice properties, and we can also go back and forth. No? I mean, from the measure we go to the Cauchy transform by the definition, but that's a way of going back, and this is the Stieltjes inversion. So the measure mu can be recovered from this Cauchy transform via what is called the Stieltjes inversion formula. Stieltjes inversion formula, which says the following. If I want to know the value of my measure, let's say on interval AB, I can get this from values of my Cauchy transform. So namely, if I take the limit epsilon going to 0, minus 1 over pi, and I'm taking the integral from a to b over the imaginary part of the Cauchy transform at x plus I epsilon. This is equal to dx. So I'm integrating this here, and if epsilon goes to 0, this will give me the measure mu at the open interval a comma b, and possibly also if the measure has mass at points a or b, I also get half of those masses. So I get the measure mu of the set a comma b. Okay, so I'm in a complex plane. The Cauchy transform is defined here. My measure lives on the real line, and essentially I want to know, the measure, let's say at point x. So, for example, if my measure has a density, then I would like to know the density at this point x. And the point is, essentially this is telling me that what I should take is minus 1 over pi, and I take the Cauchy transform at, I cannot take it at point x because it's not defining the real axis, but I can go a little bit into the complex plane. So I go to the point x plus I epsilon, and in the end I send epsilon to 0. So I take the Cauchy transform here, and then I take the imaginary part of the Cauchy transform, and with this I go to the real axis, and essentially this tells me that with a minus sign at 1 over pi, this gives me the density at this point. Okay, if my measure here doesn't have a density, I should formulate it in this form. Okay. Maybe another way of saying this is that actually when I take minus and the 1 over pi, and I take the imaginary part of g of x plus I epsilon, then this is a density or a probability measure. So this is essentially this is a perturbation of probability measure which I have here, if I'm going up to here. This is a density or probability measure which converges in a weak sense to my original probability measurement. So this converges, epsilon goes to 0, my measure in a weak sense. The convergence of probability measures, which is one formulation of the weak convergence of probability measures, is this formulation here. Okay. So this tells me essentially that I can recover my measure on such open intervals by the value of the Cauchy transform, and this also implies that actually the Cauchy transform determines the measure uniquely. So this is also maybe part of this. So if I have two measures, then their Cauchy transforms must be different. Okay, so I should not erase what I still have to prove, but okay. This we still have an idea what we should prove. Good. Okay, so in particular, if I have the Cauchy transform of a measure mu and the Cauchy transform of a measure mu are the same, then this means that mu and mu must be the same. Good. Okay, and then I have still a part 3, which actually maybe is also interesting. It's a characterization of the class of Cauchy transforms. So here I have stated that Cauchy transforms have some properties. But there is also a reverse direction. So namely, if you have an analytic function from the upper to lower half plane, which has this kind of property about the growth at infinity, then actually it must be the Cauchy transform of some measure. So this is also that actually, we can also go in backwards if we construct an analytic function which has the right growth condition, then we know that this must come from a measure. Okay, that's also important characterization, but this is a little bit hard. I will say a few words about this, but I'm not going to prove this part. The other parts I can more or less prove, but this is, for this one needs more theory and background. But the statement at least is interesting to know. So if I have a function from C plus to C minus, which is analytic function. Okay, just being analytic and going from C plus to C minus, this is not enough. What we also need is some kind of growth behavior at infinity. So namely, what we want is, it should satisfy, the Cauchy transform essentially at infinity must behave like 1 over set. So we must have a function which has also this kind of behavior. And so here we take somehow kind of property like this. So the limit y going to infinity of y times the absolute value of g of iy. So again, I'm just looking on the value of my function on the imaginary axis if I'm going to infinity, and then it should be like 1 over y. Okay, so if I have a function like this, then actually it is the Cauchy transform of a probability measure. And of course, this probability measure is uniquely determined. So then, like this unique probability measure mu such that this function g is actually the Cauchy transform of this g. Good. Okay, so let me say a few words on the proofs of this, and more or less we can prove everything, but please a bit. Definition and the statement is spread over everything. Good, okay, so the first statement was that it just goes from C plus to C minus, but this was clear, right? Just looking at the definition. The proof of point 1, the first was C minus. Okay, the second point is that actually it's an analytic function. And this is also quite straightforward to prove. I mean, there are different possibilities. One is to see that you have power series expansion about any point, or maybe if you want to check that something is analytic, maybe you just derive the differential quotient. You can see that you have a derivative. Maybe let us do this. Okay, so check that we have a derivative. So this means we should take, I want to have to see the
derivative at z, I should look on GW minus GZ for W going to Z, and then divide this by W minus Z. But then maybe let me first check what is this difference here. So this is of course the integral. So GW is 1 over W minus T. GZ is integral over 1 minus Z minus T. I'm integrating this with respect to mu. And of course this difference of those resolvents is given by multiplying here W minus T, Z minus T, and then I get here Z minus T minus W minus T, so the T goes away, and I have here Z minus W. Okay. And so you see it's now, I mean, this is nice because now if I divide this by Z minus W, this term here goes away, so we get a very nice expression. So this means we are looking at the difference quotient, GW minus G of Z divided by W minus Z. So what is this? So I divide this by W minus Z, so I just get minus sign. So this is minus. And then I remain with the integral over W minus T Z minus T du T. Yeah. Okay, now of course I send W to Z. Okay, then one has to see that this converges, but of course I mean everything is here nicely and uniformly integrable, so of course I mean this just converges to Z minus T. So this means the limit exists, and so I can write down the derivative of this function of the Cauchy transform. So this is given by minus here over R, and this here is just 1 over Z minus T squared. And this also goes to Z minus T. Integral T. Okay, so this means I have a derivative. This means my function is analytic. Of course, I mean you should check that the limit, I can move the integral, but because everything is nicely uniformly integrable, that's okay. Good. Okay, so that's easy. Good. Also, what is part 3 here? So this was this property. What happens if I go to infinity? And maybe let me prove this here. So that here was the statement. If I take the limit y going to infinity, and I take y multiplied, or I take I times y, multiplied with gi times y, this is 1. Okay, so let us check when we get this one. This is again, we just essentially calculate, what this is. And I mean, what are we claiming here? Essentially, I mean, those are complex numbers, so we are claiming this goes to 1, and this means, of course, that the real part of this goes to 1, and the imaginary part of this goes to 0. And usually we should look at the imaginary and the real part separately. So what we are actually claiming here are two things, one about the real part and one about the imaginary part. So this here claims actually that the imaginary part, y times the imaginary part of g times iy, and this goes minus 1, and y times the real part of g of iy, this goes to 0. If y goes to infinity. Because if I take the real part of this quantity, the real part of this is the y minus the real part of this guy here. Or the imaginary part of this guy is the real part of this here, because I already have mine here. So this statement here actually means those two things. So here I don't put the I anymore, because the I just exchanged real part of imaginary part. Okay, so what I'm claiming is that the imaginary part of giy for y going to infinity behaves like minus 1 over y. Okay, I should check this limit. So let us just calculate this. So let us do the first one. The second is
similar. So what I want to see is what is y times imaginary part of g iy. Yeah, okay, so let us use the definition, of course, of the Cauchy transform. So the y is just a constant, which I can move under the integral, so I have here y. And then the Cauchy transform, I'm integrating 1 over z minus t, so I should take the imaginary part of this. And of course, the imaginary part of the integral over something is the integral over the imaginary part. So I have here the imaginary part of 1 over, and to set the argument is now iy. So I have here iy minus t, and I have to integrate with respect to t. Okay, just written down, this means. So I should now see what is the imaginary part of this quantity, and of course the imaginary part of the complex number is the complex number minus its complex conjugate divided by 2i. So I should take divided by 2i. I take the number, which is 1 over iy minus t, and I subtract the complex conjugate. And of course the complex conjugate, the effect is of replace getting a minus here. Minus 1 over minus t. Okay, this here is of course, because I'm multiplying this with this, but this gives me y squared plus t squared with a minus. So I get here minus y squared plus t squared. Because I'm multiplying so this with this, which gives me this squared minus t squared. But iy squared is minus y squared, so I get minus y squared minus t squared. So I get minus y squared plus t squared. Okay, on top I get this minus this. What goes away? The t goes away, and I'm left with 2 y. And I also have from here this. Everybody can check this for himself. So 2i goes away. And I'm left in the end, so I'm left with, I have minus, I get a minus from here, which I took out of the integral. And then I have here a y, but I have another y there, which is the y coming from there. So I have here y squared divided by y squared plus t squared. And this has to be integrated with respect to t. Good. Okay, now maybe, I want to send y to infinity, and so maybe it's good to divide by y squared here. So, I'm dividing by y squared. So I have minus, and then I have my fraction here, I divide by y squared, so I have 1 over 1 plus, and here I have now t divided by y squared. T. Oh, okay, and what I want is to see what is the limit of this if y goes to infinity. And of course, the y is now only showing up here, and the limit of this, the pointwise limit of this guy for y going to infinity is very simple, because for fixed t over y goes to 0, so I just get 1. So this guy here converges, if y goes to infinity, converges to 1 pointwise over t. Okay, and of course, so we have the integral. We don't have the limit of the integral, and then we know pointwise this converges. So we can use the Lebesgue's dominated convergence theorem if we see that what we have here is a bounded function. But you see, this guy here is bounded by 1. And we are integrating, we have a probability measure, so the constant 1 is integral. Okay, so this means this thing here is bounded by 1 for t and y, so I really can use the Lebesgue's dominated convergence theorem, which tells me that this converges really from y to infinity to the integral, so I have here minus, and then I have the integral, the limit of this pointwise limit is function 1 to t, and of course the integral of function 1 is just 1 for probability measure, so I get just minus 1. in this context is really to use this convergence theorem of square integrals. But this works out nicely. No problem. Okay, the real part goes more or less the same. Similar calculations. Good. So this was this, but now maybe the more interesting thing is the Stieltjes inversion formula, which again will be a kind of exchanging limits and integrals. So, okay, so we have now moved this. Oh no, where is it? Good. Okay, maybe I also erase this part of the statement, because we are not really going to prove it. I will record it again later. This can also go away. Okay, so what are we claiming? We are claiming that we can recover the measure from the Cauchy transform by looking on the imaginary part of my Cauchy transform at the point x, but shift a little bit into the upper half. So we should again calculate what is this. So we should look on the imaginary part, the Cauchy transform at the argument x plus I epsilon. The epsilon we want to send this to 0. Okay, so what is this? So again, this is Cauchy transform is the integral, and then the imaginary part we are moving under the integral, so it's the imaginary part of 1. The argument now is x plus I epsilon. The x is real, and I'm taking minus t, so maybe I write it as x minus t. This is the real part plus I epsilon. So my argument here is x plus I epsilon, and then I'm taking minus t and integrate this with respect to t. Okay, so again I have to calculate the imaginary part of this guy here as before, and this is just minus the integral of y divided by the square of the real part, which is x minus t plus the square of the imaginary part. Okay, so that's same calculation as before for this imaginary part. And integrate this back to this. Good. And now what we are claiming is that we get, by integrating now this imaginary part over some interval, then I really get something which I can express in terms of my measurement. So let us now integrate this from A to B. So I take the integral from A to B of this imaginary part, Cauchy transform and argument x plus I epsilon, and I'm integrating this just with respect to the x, over this x. And now what is this? I'm just plugging in this. And of course I have now two integrals, 1 over r from Cauchy transform, and the one which I have here over AB. And of course and everything is nicely positive or can control. So I can exchange the integrals. So let me do this right away. So I have this minus sign here. And then I say I have to first do this integration, and then I do the integration from A to B. And what do I have to integrate? Actually, I mean, there's no y. The y is what I call the epsilon. Okay, so at some point I call the imaginary part y, but now the y is the small epsilon. This y is epsilon. Okay, so what I have here is then also epsilon divided by x minus t squared plus epsilon squared, and I'm integrating over dx and dt. Okay, I just have written it down.
And so I have now here integral with respect to dx of this function, and this is a function which we can essentially integrate, but maybe we just shift it by t and we scale it by epsilon, so that maybe it looks more familiar. So what I really have here, right, so this is minus integral over r, and then I'm integrating, so I'm shifting by t, so I'm going from a minus t, and I'm also scaling it by epsilon, so I'm dividing by epsilon, e minus t divided by epsilon, and then I'm left to integrate 1 over x 1 plus x squared. So I just have replaced x by x minus t divided by epsilon. And of course you have to take into account that I get epsilon, additional epsilon here for the change of my variables. And then I mean essentially new variables. This here is just 1 over 1 plus x squared. Okay, here also still integrating respectively. Good. Okay, I mean this integral, the integral over 1 divided by 1 plus x squared, this is something which we know, this is the arcus tangens, so the inverse of the tangents. No? So this is, we can do this integration. So this means what I get here is the inverse of the tangents at this point minus inverse of the tangents at this point. So this is tangents, arcus tangents of e minus t divided by epsilon minus arcus tangents of a minus t divided by epsilon. Okay, this is something which we can control. What happens if epsilon goes to 0? Because that's what we want. No? Epsilon, we want to go to the real axis, epsilon goes to 0, and the epsilon is now showing up over here. And again, point-wise, we see what happens here. No? So namely, if this here is not 0, then dividing it by epsilon, this goes to plus or minus infinity, depending on whether this here is positive or negative. And I mean the arcus tangents, I mean this somehow goes something like this. I mean for plus infinity it goes to pi over 2, and on the negative side it goes to minus pi over 2. So this means those values here, I mean there are three possibilities. If this here is 0, which means if t is b, or here t is equal to a, then this is 0, then the epsilon doesn't matter, and then I get a 0 here. Okay. But if this here is positive, then this here goes to plus infinity, which means this goes to pi over 2, and if this here is negative, then this here, for epsilon going to 0, goes to minus infinity, and I get here minus pi over 2. Okay. And so, according to this, so this here, for epsilon to 0, I mean gives me now three possibilities. So namely, if this here, if t is outside interval a and b, then I mean these are both plus infinity or both minus infinity, so they will just go away in the difference. So it is 0 if t is not in the interval ab. Then if t is one of those points here, if t is either b or t is either a, then I mean one of the terms will be 0 and the other one will be p over 2. So what I get here is then p over 2 if t is equal to a or t is equal to b, and if I'm inside this interval, then I will get p over 2, but here with a plus and here with a minus, which means I will get it twice, p over 2, which means I get pi. Pi if t is in the open interval. Yeah, okay. And so what I have here is again, I'm integrating here a function for which I know the pointwise limit. And again, you can see that everything is here bounded. So again, we can use the Beck's-dominated convergence theorem. And so the limit of the integral is really the integral of the limit, and the limit is this. So what I have to do is to integrate this function with this measure mu. And so you see, I mean, inside I have a constant density pi. I'm integrating constant density pi, but at the endpoints I'm also integrating pi over 2. So if this mu has a mass at the endpoints, then at each of the endpoints I'm collecting a pi over 2. That's why here we get this additional term. But if mu has no atoms, then of course this is not here. But mu can be anything. Okay, so this means the whole integral here for epsilon going to 0 already goes to minus. So we have this minus, and then in this case I get the pi, and I get the measure of the open interval. I'm integrating this function is open interval, so I get the function constant pi. I get mu of this one, and if I have mass at the endpoints, then I'm also integrating over this mass at the endpoints. So I get here 1/2 pi of the measure of the set A and B. So the measure of A plus the measure of B. Okay, so this is this formula. Good, and then we're also claiming that from this one sees that the measure is uniquely determined by the Cauchy transform. This is maybe not directly clear, because this term might look a little bit disturbing. To know a measure, I should know the measure of, let's say, open intervals. So this means if I know mu of all AB in terms of the Cauchy transform, then I know the measure. Okay, this formula almost tells me the measure of AB in terms of the Cauchy transform, but if there are atoms around, then I might have this term, and then it's not so clear whether this does not disturb my argument. But actually, because atoms, there can be only countably many atoms, so this is enough information to really see that things are really determined. So then we have this common, so let's assume that I have Cauchy transforms of two measures mu and mu. And I want to see that those measures must be the same, if the Cauchy transforms are the same. And then this formula here tells me, if I don't have this term for mu, and also not for mu, then the measure of mu of this open interval is the same as the measure of mu for the open interval, because here everything is the same. So this means that mu open interval B is the same as mu open interval B, at least for open intervals where A and B are not atoms of mu and also not atoms of mu, because then this term is absent, this extra term. So I know this open intervals AB such that A or B are not atoms mu and not atoms of mu. Okay, good. But of course I should know, the equality of the measure on all intervals, not just on those for which I have some conditions on the boundary of the interval. So actually, this is good enough, because measures have some continuity properties, which means if I know the behavior of such atoms, then I know it also for all of them. So like this, so because I can approximate any interval by intervals where the endpoints are not atoms. This is because there are only countably many atoms. A measure can have only countably many atoms because it's a probability measure, so the atoms must sum up to something, the weight of them, which is less than 1. But of course, if you have uncountably many things bigger than 0, it cannot be bound. No? Okay. So the atoms can only be countably many. So since there are only countably many atoms of mu terms of mu, so we can write any interval. We can write any
atom of one of my measures. This is not good, but I can write this as the union of intervals where I don't have atoms. So maybe I can write it as A plus epsilon n, comma B minus epsilon n as a conjugate union, where these epsilon n's are numbers which go to 0. So I mean I'm writing AB as a union of smaller intervals. But I mean epsilon, if n goes to infinity, this epsilon n goes to 0. So I mean this here is increasing, and in the end I get this. So where the epsilon n goes to 0, and I choose it in such a way that those intervals don't have atoms here. And because I mean the atoms are only countably many, I mean I can choose my epsilons such that I'm not hitting the atoms. So those guys here, those are no atoms. Okay, but this means for all of those, here I know that the measure mu of this interval is the same as the measure nu. And if I'm writing sets in this form as a union, then I mean one has monotone convergence for measures, for probability measures, which means that equality here is enough to guarantee equality here. So monotone convergence of measures, so the measure of the interval AB is actually the limit n going to infinity of the measures of the interval A plus epsilon n, comma B minus epsilon n. So this is an increasing sequence which converges to this. This is just a basic continuity properties of measures. But I mean for those sets here, this measure is the same as the measure mu of the same set. Of course, the argument which I made for mu is the same for mu, so this here converges, of course, to the measure mu of the interval. Okay, this means that mu and mu agree on all open intervals, whether or not the endpoints are atoms. And so this means, of course, that the value of a measure on all open intervals determines the measure everywhere. Okay. Then maybe let me make a remark on the third part of the statement, which I have erased, but this was saying that if I have an analytic function from the upper half plane to the lower half plane, which has some prescribed growth condition at infinity, then this actually is a Cauchy transform of something. Okay, and this follows from maybe a more general theory, which is about describing analytic functions, let's say from C plus to C plus, or C plus to C minus, or maybe the disk to the disk. So I mean there's a whole theory about this, that if you have analytic functions from, let's say, upper half plane to upper half plane, then they must be of a specific form, which is not so far away from Cauchy transforms. So I mean, being analytic is a quite rigid condition. And if you want to be rigid on big domains, then there are not so many possibilities. If you're really analytic, not allowed codes or something like this. In particular, I mean, there's a theory of Levandina, so Levandina theory about such functions, and from this, the results about the Cauchy transform follows. So this follows from results of Levandina, but I mean that they are not trivial, so I'm not going to say more about them. Results of Levandina about analytic functions. Let's say here a function from C plus to C plus on the upper half plane to itself, and this Levandina theory tells us that any such function is of a very specific form, so namely, and here I don't have a growth condition, so any such phi is of the form phi of z, so it can be a constant function.
of course, then it can be a linear term, beta of z. But then, of course, I mean, higher order terms are not so clear, because I mean, if you want from C plus to stay in C plus, you cannot just take the square, for example. I mean, if you square, you spread C plus over all of C. So that you want to stay within C plus is quite some condition, and actually, I mean, what you need are functions of the form which are not so far away from Cauchy transforms. So we have here another term which is of the form R, 1 plus times z divided by t minus z, and you are integrating here with respect to a measure. Okay, the statement is any such function that exists alpha and beta, which are real numbers, and this beta must be positive, otherwise this wouldn't work. And here you have a finite Borel measure. So you have somehow average over functions like this. So those are typical functions which have this property. So this means for those alpha, beta, and sigma, and they are also uniquely determined. So for unique finite Borel measure sigma are and alpha and beta real numbers, and the beta must necessarily be greater or equal to 7. Okay. So a general function, and now we have a function from C plus to C minus. So I mean, we would have a negative version of this, but then we also have in addition this growth condition. What happens at minus if you go to infinity, and this of course gives you some more restrictions. So on those numbers here, and also on this. And essentially, I mean, you can rewrite this, and you see that actually this you can rewrite as a Cauchy transform of a probability measure, and this probability measure is of course coming somehow from the sigma. The sigma here is not a probability measure; it's just a finite measure. But you can check for yourself. If you start from this, then the rest is again maybe just checking what it means. That you have this growth condition on this quantity. It gives you some extra condition, which in the end tells you that you can rewrite this as a Cauchy transform. Okay, and so that's again a collection of results about our main analytic object, so the Cauchy transform. But now we should maybe go into the direction of connecting it with our moments. So this was just a probability measure, but clear from the definition that actually what I have here is more or less a generating function in the moments. So namely for our compact and supported measures at least, this Cauchy transform has a power series expansion, and the coefficients there are the moments of that's last thing which we watch today. So position. And this power series expansion, for this I need compact support. I mean, in general, there doesn't have to be a power series expansion, but if mu is compactly supported, let's say in the interval for minus r and plus r, so the measure of minus r plus r is equal to 1, no mass outside this interval, for some r bigger than 0, then this Cauchy transform has a power series expansion about infinity, which means essentially it has an expansion 1 over set. I mean at 0, I mean at the real axis it somehow can explode. So the nice behavior is at infinity where we can control everything. There it behaves more or less like 1 over set. And about this point it has a power series expansion in 1 over set. So the statement is then G mu. That's power series expansion about the point infinity, the more mobility
is, it can be written as a series of the form summing n from 0 to infinity, and then I have some coefficients mn, and I'm dividing by z divided by n plus 1. Okay. And this really is a convergent power series if the set is large enough. So this means the power series is about infinity, not for small set, but for large set, because this is something in 1 over set. So I'm claiming that this is a converging power series now if z is really strictly larger than this r, and this mn here are really the moments of my method. So where mn are the moments of my measure. So it's the integral over t to the n with respect to my measure on r, of course effectively only for minus r to plus r on the complex interval. Those are the moments. So this means what we have here is really it's a variant of this, what we call M of Z, this moment series before, but it's a variant which has very nice analytic properties. And the proof of this, of course, is very straightforward. Using the definition, the Cauchy Transform, and just doing a power series expansion of this 1 over Z minus t. So if Z is large enough, if it's larger than R, then we can extend this 1 divided by Z minus t. That's what we have to integrate in the Cauchy Transform. And this is a geometric series, which I just should write it in this form. So it's 1 divided by Z 1 minus t over Z. So this is Z minus t. Okay. And so you see this is now a geometric series, and what I need of course is that this t divided by z is strictly less than 1. Then I have the power series expansion of this, and to guarantee this I should make the set large enough because the t over which I integrate are really less than r. So this here really gives me the power series expansion. I have this extra 1 over z here, and then here I'm summing from 0 to infinity is t divided by z to the power n, and this works for all t in the interval from minus r to r, and that's the interval over which I have to integrate for mu, because mu only has support there. So for all t, this here really converges if the set is strictly larger than this r. And this conversion is actually also uniform, so this means I can exchange integration and convergence. So the convergence is uniform in this interval. So hence, my Cauchy transform of z, which is the integral, let's say this integral really only goes from minus r to plus r, and I take 1 over z minus t, but now I can write this as this infinite sum, and then, because of the uniform convergence, I can exchange the integral and the sum. So this really is then the same as the sum, and from 0 to infinity, I have the integral from minus r to r, and what do I have here? I have t to the power n, and I have z, I have here 1 over z to the n, and here I have an extra 1 over z, so actually I have here z to the n plus 1. And now, of course, the set has nothing to do with the integration, so I have here just the integral over t to the n with respect to the mu, this is the nth moment, and then I have exactly the expansion which I'm doing. The sum n from 1 to infinity, the nth moment, which is this integral over this, and then I'm remaining this divided by z to the n plus 1. Okay, and so now we really see this connection between the Cauchy transform and the moments. The moments, before we put this in this form of power series m, but here essentially we are saying we should change the m a little bit. This here is more or less like the m, but it's more like 1 over z instead in terms of z. But in this form, the analytic behavior of this power series is much better. theta. So that's the reason that we are going to reformulate things which we had before in terms of M and also in the C for the Cumulus series. We are going to reformulate it in terms of this Cauchy transform, and then the C series we will also make a small shift and rename it to R and call it the R transform. And then we have to ask the question, the R transform is also analytic and things like this. And can we, in the long run, we also want to see, can we extend this relation between moments of cumulants or between the Cauchy transform and the R transform also to measures which don't have compact support. Good. Okay, so let's stop here.